Roboflow has introduced RF-DETR, a state-of-the-art real-time object detection model. RF-DETR is a transformer-based object detection model architecture where RF represents Roboflow and DETR represents the detection transformer. RF-DETR outperform all existing object detection model on real datasets, and it is the first real-time model to achieve 60 plus mean average precision when benchmarked on the COCO dataset. RF-DETR achieves a state-of-the-art performance, beating models like YOLO 11 and YOLO V8 on both COCO and the newly introduced RF-100VL dataset. So by scaling the resolution to 728 pixel, RF-DETR achieves 60.5 mean average precision at 25 FPS on NVIDIA T4 GPU. Like you can see over here, RF-DETR model, DETR large model achieves a 60.5 mean average precision score on an input resolution of 728 pixels. Okay, so we can say that your RF-DETR is the first documented real-time model to break the 60 mean average precision barrier on the Microsoft COCO benchmark. So RF-DETR comes in two model sizes, RF-DETR base model with 29 million parameters and RF-DETR large model with 128 million parameters. So to do object detection on images and on videos, you can just install the RF-DETR package by just writing pip install RF-DETR, and then you will be able to do object detection on images and on videos. So here you can see we have the code to do object detection on image using the pre-trained RF-DETR model, and here you can see we have the code to do object detection on a video using RF-DETR pre-trained model. You can also use a custom model and just add the custom model weights, and you can also do object detection on a video as well using any custom model. Okay. So now here you can see if you want to do object detection on a live webcam feed using RF-DETR, you can use this code. Okay. So like here we have the code for the video inference. So if you fine tune the RF-DETR model on any custom dataset, for example, potholes for personal protective equipment detection, for license plate detection, you can just add the fine tune model weights, and you can just run the fine tune RF-DETR model on any video as well. Okay. So here you can see that RF-DETR is available in two variants, RF-DETR base model with 29 million parameters and RF-DETR large model with 128 million parameters. Okay, the corresponding COCO pre-trained checkpoints are automatically loaded when you initialize either class. Okay, so like you can see over here, they have just given a quick trick so that you can improve the results. Both model variants like base and large model sports input configurable input resolution. Like you can just configure the input resolution. A high resolution usually improves the prediction quality by capturing more detail, so it can slow down inference. So if you just set the high resolution, it will give you better results, but we will slow down the processing like inference. You can adjust the resolution by passing the resolution argument and initializing the model. Resolution value must be divisible by 56. So whatever resolution value set, it must be divisible by 56. Okay. So in order to fine tune the RF-DETR model on any custom dataset, RF-DETR expect the dataset to be in the COCO format. So you should reformat your dataset in COCO format to fine tune the RF-DETR model on any custom dataset. So for fine tuning RF-DETR, expect the dataset to be in the COCO format, and you can just see the COCO format over here as well. And here you can see that complete steps are provided. Like you can just import the RF-DETR base model, then you can just initialize the model, and then using train function side supervision, or you can just path the dataset path over here, and you can just set the epochs. You can also set the batch size, and you can also set the learning rate and accumulation steps as well. Okay, so here's a quick look. Like currently I will be using a Google Colab T4 GPU, and it's free to use. So on a smaller GPU, basically T4 is a smaller GPU, you can use batch size 4 and grade accumulation steps as 4. We use a method called gradient accumulation, which lets the model simulate training with a large batch size by gradually collecting updates before adjusting the weight. Or if you have a paid subscription on Google Colab, and you can access the 800 GPU, and there as it is a powerful GPU, you can just increase the batch size to 16, but you can decrease the graduation accumulation steps to one cost. uh the product of batch size and graduate accumulation steps should be equal to 16. Okay. Okay, so like you offer multi-GPU training as well, and then you can just do a prediction by loading the pre-trained model weights. Like here you can see that uh, you can just follow this step and load the pre-trained weights, and then you can just do the prediction as well. Okay, so you can also convert your RF-DETR based model to NX format as well. You can just see that, and here all the acknowledgements. Okay, so let's get started with this. Okay, so here you can see that I have just prepared a Google Colab notebook over here. So here I have just written out all the steps that are required to fine tune or train the RF-DETR object detection model on any custom data set. Before we run the script, please make sure that you have selected the runtime as T4 GPU. Okay, so first we need to set up the environment. So to download the model weights, you need to provide your Hugging Face token. So you can just click over this link and you can just go to Hugging Face settings from here. And if you haven't created your account on Roboflow, you can create your account on Roboflow. Then you can click on Access Tokens from here, and you can just click on Create New Token from here. Uh, you just write the name of the token, the ATR. Then you can just click all these checkpoints from here. Okay. Then you can just click on create token from here. You can just copy this from here. Then you can just click on the secrets key from here. Okay, and here you will just write like we can delete the previous token, and you can just click on add new secrets. Okay, so you can just write the name as Hugging Face token, and you can just change this name as well. No worries. Then you can just add this token value over here. You can just uh, check this as well, and then you can just run this cell from here. Now I'm just providing the access to now I'm just providing my Google Colab access to my Hugging Face token. Okay. Okay. Okay, so I just need to go over here and just run this provide the notebook access over here, and now just check this as well. So now you can see that it has the access. So please make sure that you are using the Google Colab offers free GPU. So you can just go over here and select the runtime as T4 GPU, and you can use it. So please make sure that you are using the GPU memory. So I'm using the GPU memory. So to do object detection on images and on videos using RF-DETR, or if you want to fine tune the RF-DETR model on a custom dataset, you need to install the RF-DETR package. So we will now install the RF-DETR package. So the installation will take few minutes. So let's wait for the installation to get finished. The package installation is completed. So I will just go ahead. So now we will download the dataset from Roboflow. I will be fine tuning the RF-DETR model on Potholes dataset that is available on Roboflow. You can just click on this link and it will redirect you to the dataset on Roboflow. So if you haven't created your account on Roboflow, you need to create your account on Roboflow so that you can download this dataset from Roboflow into your Google Colab notebook. Okay, so this is my dataset over here. My dataset consists of 665 images of potholes. Okay, and you can see that all these images are annotated. We have only one class, which is potholes. Okay, so you can see all the images are being annotated, and here is a quick overview of my dataset. Overview of the dataset. Okay, so we have 665 images in total. As in general computer vision practice, we take 70% of data for the training purpose, 20% of the data for the validation purpose, and 10% of data for the test purpose. I have taken 465 images for the training, 133 images for in the validation set, and 67 images are in my test data set. And in the pre-processing, I've just resized all my images to 640 cross 640, and no augmentation is applied on the training data because I have only one glass, which is pothole, and this image size is enough for this data set. Okay, so let's go ahead and let us download this data set. If you want to export this data set or download this data set from into your Google Colab notebook, we just need to click on the download button, and you can just click on download data set from here, and you can just select the format. Okay, so currently you can see that as I told you that uh, RF-DETR expect the dataset to be in the COCO format. Okay, so we'll just set the format as COCO, and I will just click on show download code from here, and I will just copy this code from here. I will just add this code over here. So this will download the dataset from Roboflow into the Google Colab notebook. So now you can see it's downloading the dataset from Roboflow into your Google Colab notebook. So it's done, and you can just close this from here. Okay. So now you can see we have the potholes detection dataset, and if I just open the YOLO V12 GitHub repo from here. Oh no, I just need to open the RF-DETR GitHub. Okay. So here you can see we have the RF-DETR GitHub repo. So like you can see over here, uh, our RF-DETR model expect the dataset to be in the COCO format, and it should be in this format. Okay, so you can see that for the test, we have this annotation.coco.json file, and we have the images. So you can see we have the annotation.coco.json, and we have all the images. For the training, we have the annotation.coco.json, and we have all the images. And for the validation, we have the annotation.coco.json, and we have all the images. So our dataset is in the format what RF-DETR expects. Okay. So now we can just check the dataset location. So our dataset is in this location, and we can just see it over here as well. Okay. So now we just need to train the RF-DETR model on custom dataset. So I have already provided you that all these details, like you just need to choose the right batch size. So when I was just explaining the GitHub repo of RF-DETR, I just explained you that as we know, you know that we have a T4 GPU, like it's a smaller GPU. You need to set the batch size 4 and where accumulation steps is equal to 4, because we want the product of these two to be equal to 16. Okay, like the key is to keep their product equal to 16. And if you have a powerful GPU, like if you have a Google Colab paid subscription, you will have access to 800 GPU. If you have the access to 800 GPU, then you can set the batch size 16 and where accumulation step is equal to 1. Okay. So I have already trained the R or fine-tuned the RF-DETR model on this potholes dataset. So now I will not start the training process again. Okay. So I will just show you, like I have just set the dataset location over here. Like you can see that in the dataset location variable, we have the dataset location. Okay, I have fine-tuned the RF-DETR model for 30 epochs on this potholes dataset. We have set the batch size 4 as I have a smaller GPU, T4 GPU, and grade accumulation step is equal to 4. So the product of these two will be 60. And we have set the learning rate over here as well. So I have fine-tuned the RF-DETR model on potholes dataset for 30 epochs, like you can see over here. Here you can see we have all the training process. Okay. So you can see over here, we have all the training process we provided over here. Okay, so let's look at the results below. Okay, so like you can see over here, we have the training and validation loss graph over here. So you can see that as the number of epochs are increasing, like Let's see over here, training and validation loss both are decreasing. We can see over here. So this is a good thing. So next, we will look at the average precision and average recall graphs. Like you can see over here, we have calculated average precision over different epochs at IoT thresholds ranging from 0.50 to 0.95. So we have the average precision and average recall graphs. So the graph below represents the average precision over training epochs across different IOU threshold, which are ranging from 0.50 to 0.95 in a step of 0.05. Okay, so like before we discussed the average precision and average recall, what they interpret, we need to know what is average precision. Average precision is a key metric used to evaluate object detection models. It measures how well a model detects objects across different confidence thresholds by considering both precision and recall. Okay, so average precision is calculated by considering both the precision and recall. So what is precision? Precision is the number of true positives like correct prediction out of all predicted object. Like in precision we find like how many correct predictions are there out of all the predictions made. In recall we find how many correct predictions are there out of all ground truths. Okay, so to calculate the average precision you just need to create a precision recall curve, and precision recall curve is plotted at by varying different confidence threshold. Then basically the area under the precision recall curve is the average precision, and higher average precision mean that our object detection model or fine-tuned model is performing better. Okay, and if we just see over here, our average precision is around 0.640. Okay, like you can see over here, our average precision is around 0.60. So like you can see, our model average precision value is around 0.60, which is relatively high, indicating decent object detection model capability. Okay, so model stops improving after 10 epochs, meaning further training may not bring substantial gains. Like you can see over here, our model stops improving like after 10 epochs, and we're providing around the same average precision. So if you want to further improve that results, you can just increase the size of your training data by applying augmentation. Okay, so next graph we'll look at average recall graph. So like over here we have the average recall graph, but before we discuss the graph we need to know what is average recall. So the graph below represents the average recall over training epochs across different IOU thresholds. Like you can see that so this graph represents the average recall over different training epochs across different IOU threshold, which are ranging from 0.50 to 0.95 at a step of 0.05. Okay, so you can see that average recall starts at a very low value. Like you can see over here, the average recall starts at around 0.19, and then it improves in after few epochs. Okay, so uh, the average recall starts at low value and increase rapidly in the first few epochs. It stabilizes around 0.3 to 0.34 with minor fluctuations. Like you can see over here, it's stabilizing between 0.23 to 0.34 with minor fluctuations. That is correct. Okay. The trend suggests that model is learning effectively, but may still be improving gradually. Like if you train on high epochs, like average recall can further improve. So what is average recall? Average recall is a metric used in object detection to evaluate models' capability or models' ability to detect object across different IOU threshold. Uh, so every recall is just tell us the object detection model ability to detect like object like across different IOU threshold. So how we calculate the average recall? Average recall is measured at multiple IOU threshold. Okay, the average of the recall it gives the average recall. So we just calculate the average of the recall values at different IOU threshold. So once first we calculate the recall score at different IU threshold. Like we calculate a recall score at 0.50, at 0.55, 0.60 at different IU threshold. Then we take the average of those recall values that are calculated at different threshold, and this gives us the average recall. As I told you that average recall is the number of true positives that are found out of all ground truth annotations. Okay. So, what is IOT threshold? Like IOT threshold tell us like how is the threshold is the ratio of overlapping area between the predicted bounding box and the ground truth bounding box. Okay. So if we set the IOT threshold to as 0.5, so if the overlapping area between the predicted and the grounding bounding box is uh, is above the threshold, if the IOT threshold of the predictive bounding box and the ground truth bounding box is above 0.5, then we will say it's true positive. So if we have set the IU threshold to 0.6 and if the overlapping area of the predicted bounding box and the ground truth bounding box is does not if the IU threshold of the predictive bounding box and the ground truth bounding box is 0.3, then we can say that this is not true positive and this is false positive because our IU threshold is uh, 0.6 which is set. Okay. So higher average recall indicates that the model detects more objects across various IO threshold. Okay. So you can see here we have the average precision and average recall graphs. You can see over here. Okay. So now we can also test the fine-tuned model on test data set as well. So we have not used the test data set images in the training. So you can always test your model on the test data set images and see how it performs. And here you can see we have the sample image. Like you can see in our annotations, these two potholes are being missed, but our fine-tuned model detects these two potholes as well. Okay, so it's giving good results. Okay. So like you can see over here, there are some more results. Like you can see that we are able to detect the potholes and the results look quite promising as well. So over here, you can see that we have the mean average precision graph. So like you can see that we have the mean average precision score when IOD threshold varies from 0.5 to 0.95 is 0.46 and mean average precision at IOD threshold of 0.5 is 0.67 and mean average precision when we have IOD threshold of 0.75 which is strict IOD threshold is 0.52 and mean average precision score when we have IOD threshold varies from 0.5 to 0.95 for small objects is 0.06 like 6% and mean average precision score when we have a IO3 threshold of 0.5 for small objects is 8%, and mean average precision score when we have a IO threshold of 0.75 for small object is 0.08, like 8%. But for medium objects, the IOU, the mean average precision score significantly improves to 31%. For medium For medium objects, the mean average precision with IOU threshold of 0.5 is also further improved to 0.48. And when we have a strict IOU threshold of 0.75, the mean average precision score for median object is 0.32. And for the large objects, the mean average precision is super high. Like when mean average precision when IOU varies from 0.5 to 0.95 for large object is 0.64, like 64%. When mean average precision score when we have IOU threshold of 0.5 for large object is 0.86 and mean average precision score when we have a strict IOU threshold of 0.75 or 75% for large object is 74%. Okay. So here we have the confusion matrix. Confusion matrix basically tells us how our model handles different classes. So here you can see we have the true positives as we have 134 true positives. So what is true positive? Uh, the model, so what true positive is that model predicted a label and it matches correctly with the ground truth. Okay. So for example, model predicted that there is a pothole and so in case of like 134 times, the model predicted that there is a pothole and there was a pothole in our ground truth annotation. So we can simply say that 134 times when our model predicted a pothole, there was a pothole. And we have 27 false positive, which we can say that 27 times when our model predicted a pothole, there was no potholes. Okay. And we have 55 as false negatives. So what are false negatives? So model does not predicted a label, but there was a ground truth. So 55 times there was a pothole, but our model was unable to detect a pothole. Okay, so this is how Configure Matrix telling us that 134 times when there was a pothole, our model predicted it correctly that there is a pothole. 27 times when there was no pothole, our model predicted that there is a pothole, while 55 times, like you can see, this is false negative. 55 times there was a pothole, but our model was unable to predict that there is a pothole. Okay. So now we will run inference with custom model on video. So you can just simply download a demo video from Drive into this Google Colab notebook over here. So I have downloaded a demo video from Drive into this Google Colab notebook, and I have already run predictions using fine-tune model on this video. And here you can see we have the output video. Let me just show you the output video over here. Let me just navigate my screen towards the output video, so we can just see how our results are looking like. Okay, so here you can see here is my output video. So you can see we are able to detect the pothole, and our detection results look quite promising. Like we are able to detect the potholes. Like I have done this pothole detection using YOLO model, but the YOLO model does not detect the pothole so much accurately. Like the RF-DETR model detects pothole more accurately than the YOLO model. Okay, so like RF-DETR model is giving us outstanding results. Like you can see that we are able to detect different potholes. Okay, so our detection results were very promising. Like we were able to detect the potholes. So the Roboflow RF-DETR GitHub repository, we have seen that how we can load and run the fine-tune model. So when I train the model, or when I fine-tune the model RF-DETR based model on Potholes dataset, I save the model weights on my drive. So I will now download that weights from my drive into this Google Colab notebook, and I will show you how you can load and run the fine-tune model. Okay, so you can just save the model weights into your drive, and you can just download those weights into your Google Colab notebook, and you can just uh, load and test your fine-tune model as well. So here you can see that if you just go to potholes, you can just go to test dataset images. You can just copy the math of any image, and you can just add this over here. And here you can see that in the pre-trained weights, I am just loading my best model weights over here. Okay, and now I will just run this, and let's see if we are able to detect the pothole. So you can see that we are able to detect the pothole in this image. Like you can see the results look promising. Like we are able to detect all the potholes that are in this image. You can follow the same process, and you can also uh, test the fine-tune model on video as well. So that's all from this tutorial. In this tutorial, we have seen that how we can fine-tune the RF-DETR model on any custom dataset. In this tutorial, we have fine-tuned the RF-DETR model for pothole dataset, and our results look very promising. And what I can see is that RF-DETR model performs better than YOLO model, and we have I have practically seen in this case as well. Like for potholes, RF-DETR model gives better detection results than the YOLO model. So that's all from this tutorial. Thank you for watching.